I forgot to hit record. It is now. Thank you for pointing it out. I have to figure out a way to see everything, both the PowerPoint and the Zoom meeting, and so I can read everything. And I haven't done that yet. I'm sorry. Maybe I need a huge screen where I can see everything. If I miss something, please point it out to me. That's wonderful. So let's look at PowerPoint number 4.
Question in regards to the homework. Are we going to go over the homework or towards the end? Or?
Well, the homework is not due yet because we haven't finished the first chapter.
Okay.
All right. So, I mean, I asked you to do some of the questions that we had already covered, but because we haven't finished the first chapter, the first homework is not due. So we're not going to go over it until it's due because I don't want to answer questions that people haven't looked at yet. Is that reasonable? I hope so. Okay. So on page 4, people often wonder how polls can be accurate when they weren't asked for your opinion, right? You ever read on the news that, so-and-so has a 70% chance of winning this election, whatever it is, and you're like, well, they didn't ask me. How accurate can that possibly be if they don't ask me? Now, the question is, how do we trust it? So a Gallup poll asked a random sample of Californians whether they believe that teachers in the city or area where they live are well respected. Now, personally, I know that I am not well respected, so my answer is probably not so much, but maybe I'm the special case. Assume that if every Californian had been asked, 75% would have said yes. So just assume that. It's probably not true, but let's just go with it. So the graph below illustrates what might have happened as Gallup collected its sample. What do you notice about the beginning of that graph versus the end of that graph in relation to concepts that we spoke about on Monday? What do you notice?
Professor, we cannot see your screen right now.
No, but you have your own PowerPoint.
Oh, okay.
Yeah. The reason I gave you the PowerPoint is so that I can see you and you can just follow along on your own PowerPoint. So everyone should have their PowerPoint open, correct? Right? You all have it on Canvas. So you should all be on.
I can't see it. It won't open, so no.
Is there any way you can still share it?
Yeah, I can still share. I can still share. I would like to not share it so that I can see you guys. Plus this way I can't, I guess I can still see text if I do something, but.
Well, Professor, there's a way where you can kind of move the shared screen to resize it so that you can see more people.
What? That's crazy talk.
I think when you're on Zoom, I don't know if it works while you're sharing, but.
All right. Well, we'll try to figure that out as we go along. But ideally, we get to the point where the PowerPoints work for everyone. If they're not working for you, stick around at the end, and we'll try to figure out why. Because they are working for some, if not all. So hopefully we'll figure that out. But can everyone at least now see my PowerPoint, if not your own?
Yes.
Okay, so here we have a Gallup poll. So I ask again, what do you notice about the left side of the poll versus the right side? Question? Oh, what do you notice about the left side versus the right side?
Left side is very erratic.
Exactly.
Yeah.
Exactly. The left side is very sporadic, whereas after a while, what do we see? It's stabilized. Now, if Gallup had only asked, let's say, 100 people, then you'd see a lot of this sporadic nature, and it never would really have gotten to a point where you say, oh, okay, it's stabilized. So you have to make sure that your poll is large enough to trust it. How do you know what's large enough? Well, that's something that we're certainly going to learn about this semester. Okay, there's literally you could say a specific number is good and anything less than that is bad. We're going to get to that as the semester progresses. But anywho, if Gallup stopped after asking 100 people, what would be the estimates of the proportion of California adults who would say yes? What do you say to that? Gallup had stopped after 100. What would be your answer?
About nearly 90.
Yeah, somewhere over 80% looks like. It's hard to see exactly, but yeah, 80+%, right?
Mhm.
You all agree with that?
Yeah.
Well, what about after 500 people?
Like 7.5-ish.
Well, 0.7 is 70 something, not 7, right?
Mhm.
0.7 is 70%. So what would you say, about 75%, give or take?
Yeah.
It certainly seems that once you've reached 500, it's pretty accurate. In fact, from 500 to 1,000, what do you notice?
It's pretty steady.
It's pretty steady, right? You've reached the point where it really has stabilized from that point forward. And that's the goal. When you're taking a poll, you want to have the poll be large enough that you've reached stabilization. Because how do you trust anything less than that? Now, Gallup actually used a sample size of about 600. Does that seem accurate based upon what you see in front of you?
Yes.
Yes, because by the time we've reached 600, we essentially have.
No.
No, it's
Oh,
not.
yeah. Actually, no, it would be accurate.
It would be accurate, but between 600 and 1,000, I really don't see that much of a difference. Okay.
Yeah.
So, new example. Your 6th grade class began to flip a fair coin. The first 6 flips are all tails, as shown in the graph below. So 2 of your students disagree on what will happen next. Ava says the next flip is more likely to be heads than tails, because by the law of large numbers, it should be even, so it's got to come up eventually, right? Right? It's got to end up at 50%. So if I get 6 tails in a row, the next one's probably going to be a heads. And Pablo says the next flip is equal. It could be heads or tails. How does a coin remember what happened to 6 flips before it? Who's right? The one who's going by the law of large numbers, Ava? Or is Pablo correct when he says that coins have no memory? Which student is right? And how might you convince the class of this? What are you thinking?
Aren't they both right?
Well, they can't both be right, because one is saying that it's more likely to be a heads, and the other one is saying it's equally likely to be heads or tails, right? So those are 2 statements which cannot both be true.
I feel like Pablo could be right, only for the fact that, like, it all depends on the flip.
Yeah.
Like, if someone flips it, like, one way, most likely it'll land on heads. If someone flips it a different way, it could land on tails. But it also depends on, like, the coin, too. Like, or, like, on Monday, we saw, like, the curved coin.
Right, but we're assuming here for this example that it's, I mean, the very first line says your 6th grade class begins to flip a fair coin.
Yeah.
Right, so we're assuming here that there's no, shenanigans, double-sided coin or anything like that with tails on both sides. It's a straight-up fair coin.
Mm-hmm.
Okay,
I
so.
it depends on the gravitational pull when someone throws it.
Well, okay, so that is true. I mean, there's you could talk about the winds, you could talk about the rotational. I mean, there's so many things that you can go into, but we're just going to assume that when you flip it, you don't take any of that into account.
Well, if it's random, then the law of large numbers applies.
Well, so the law of large numbers says that the long-term behavior should reach stabilization, correct? Right? That's what the law of large numbers says, right? Long-term behavior is stabilization, right? But it says nothing whatsoever about any specific flip. It's a little paradoxical. In the long run, it's going to be 50-50. But any specific flip, it says nothing about. Which means Pablo is correct here. The next flip is just a flip. It's like if you walked into the room after the first 6 flips and you didn't even know that anyone had flipped it 6 times and someone says, hey, I'm going to flip this. What do you think is going to happen? You would say, well, it's a fair coin. It's 50-50. You're not going to say, well, what happened in the past? The past is irrelevant. This coin is a fair coin. Any specific flip, it's 50-50. Now, if you're a betting person, you might say, well, 6 tails in a row, I'm betting heads on this one because, come on, 7 tails in a row, that's never going to happen. but that's using your emotions and that's not using your brain. Your brain should be saying it's 50-50, irrelevant of what's occurred in the past. Now, I've gone to Vegas and I've lost 1,000 money betting on emotion. Let me tell you, a lot of money, okay? It's easy to get trapped into thinking, oh, I've lost the last 8 hands in blackjack. I got to win this one, so let me bet 10 times as much. It's easy to get trapped into that kind of situation. But unfortunately, even if you do that, you're still just as likely to win as lose, as my bank account has proven.
Would
Okay?
we ever have a question like this on a test?
Yeah. I mean, now that we've covered this idea, why not?
Would the answer just be like, it's a fair coin?
The answer is it's 50-50.
Okay, thank you.
The answer is straight up it's 50-50. Okay.
I have a question about that too.
Yeah, go ahead.
So is it just because like every single flip you can't predict, but over the course of time, like if they flipped all 40, it's not a whole lot of flips. It's not like over a big, a large amount of time, but we'd still expect it to be sort of like equal. Is that right?
So that's the thing. It's very paradoxical. The idea that any specific flip you can say nothing about.
Yeah.
If you give me lots of flips, I can predict a lot.
Okay.
If you flip it 40 times, it's going to be somewhere near 2020. I mean, it'll unlikely to be exactly 2020, but it'll be somewhere near 2020. I mean, yes, is it possible to be really unlucky and get 38-2? Yes, it's possible. It's just so unlikely. I'm not sure how deep into the math we're going to get this semester, but I can tell you it's very unlikely. Okay, well, I'm glad we had that talk. It's very unlikely to be anywhere that's too far away from 2020.
Okay.
But any specific flip, I can say nothing about.
Okay, got it.
Okay, very, very paradoxical. So the class continues to flip. Complete this table, giving your best prediction for the number and proportion of heads they will get after the given number of flips. Now remember, the first 6 flips were tails. So after flip number 10, how many heads do you expect there to be?
Like an exact number?
Exact number. Okay, the first 6 flips were tails. You're then going to flip it 4 more times for a total of 10. And the question is, how many heads do you expect to see after 10 flips?
6.
Well, how do you see 6 heads if there's only 4 more flips and you have no heads yet?
I expect at least 3.
Include.
Can you please repeat that? The sound is breaking up a bit. Yes. So the question is, you've already flipped it 6 times and you've gotten 6 tails. You now flip it 4 more times, and the question is, how many heads do you expect to see?
How many heads
least 2 or
before
3.
you get to 10? So
I'm sorry, I didn't hear that. Say it again.
how many heads before you get to 10s?
No. After the 10th flip, after the 10th flip, 6 flips have gone by. You've got 6 tails. You now flip it 4 more times for a total of 10. How many heads would you expect to see after 10 flips, given that the first 6 were tails?
3.
Okay.
You can't predict?
You can't predict. No, you can't predict. 100%. You can't predict. There's no way to
But
predict.
it should be like around 3 or 4 if it eventually becomes 50-50, right?
Sure. It could be somewhere around 3 or 4, but my personal guess is the following. The 4 flips that are coming, what is the most likely outcome with those 4 flips, would you think? What's the most likely outcome with those 4 flips?
Hopefully to get at least 1 head.
Okay, we definitely well, I don't say definitely, nobody cares. We would think that we would get at least 1 head, because to get 10 heads, 10 tails in a row is pretty improbable, right?
Mm-hmm.
However, if it's really 50,
Okay, can we turn the mic?
yeah, what is that?
Thank you.
If it's truly 50-50, with those 4 flips that are coming, what do you think is the most likely outcome?
He's frustrating.
Sorry?
They're all heads.
Well, if it's 50-50, why would they be all heads for 4 flips?
What do
So two.
I would think 2.
Two.
Good evening, Professor. Okay, I'll look at that later. I'm sorry, say again, what? So, I wish I can't really draw, but the law of large numbers says that in the long-term behavior, you're going to expect to see the correct proportion, right?
Right.
That's the law of large numbers. Now, the correct proportion is 50-50. So after 1,000 flips, let's go to the last one first. After 1,000 flips, ooh, did someone just write 2 in there? Was that there the whole time?
No.
Just
No, somebody wrote that. And surprisingly, it doesn't show that who does it.
You
That's
just
kinda
go
weird.
to the options and annotate, and then you can draw on the actual slide.
Yeah, but I didn't do that.
I did that.
That's awesome. Okay, you're the official writer, I guess. But anyway.
Oh, okay.
No, I'm just kidding. You're not the official writer. It is.
So next to like where you press record, I think says more options.
I press record. Where am I looking?
Like on the top where the bar is.
More. Okay.
And it says more options.
Did I miss it?
Because where I'm seeing it's green, like there's a green bar saying you are viewing David.
Okay.
Yeah, I got kicked out of the meeting for a second.
And then it says more options next to it, and you could put annotate.
Oh, so now there's 222 now. Okay, that's awesome. Everyone wants to disprove
It says view options on top.
2. I see mute, stop video, security, participants, new share, pause share, annotate.
Yeah.
Okay, annotate. So draw.
And then you draw it. Yes.
Awesome.
You got it, Professor.
Oh, I'm smart. What can I say? And how do I get rid of this? How do I get rid of this other one?
Oh, they have to erase it. Like I erased mine, so.
Oh, so I can do undo. This is so cool. Okay. Anyways, so let's go to 1,000 first. I expect after 100 flips to be somewhere in the vicinity, we'll say approximately 500.
So would it be 50-50 every time, you would think?
Well, it can't be 50-50 every time, because if you only do 1 flip, how's it going to be 50-50, right?
True.
But
But then how do you get 500? Sorry, I'm just a little bit lost.
No. It's just that the law of large numbers says that after you flip it lots and lots and lots and lots and lots of times, it should stabilize around the appropriate proportion. And because it's a fair coin, the appropriate proportion is roughly 50%.
So
right?
by 1,000, it would have stabilized.
It should be. 1,000 should be enough, somewhere in the vicinity of 500. Now,
So
do you think?
every answer would just be like approximately half of it?
Yeah, exactly.
So like for number 1.
Well, so number 1 is a little different, because here's the situation. We had tails, 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 and then tails, right? Those are what we were given. And then we have 4 more flips. So let's focus only on those 4 flips. I expect half of those flips to be heads and half of those flips to be tails. It's not guaranteed, of course, but it's what I expect. Right? I expect half of them to be heads and half of them to be tails, right?
Yeah.
Which means I expect that 2 of these are heads and 2 of these are tails. So that after 10, I'll probably have a total of 2 heads, 6 tails. And
I
then,
have a question, Professor.
Yeah.
Wouldn't that also apply for like the 1,000 mark? So wouldn't we have already had gone 6 flips?
Yes.
1,000 minus 6, divide that between 2, and right?
100%, which is why I'm not saying it's exactly 500. I'm saying it's approximately 500. Right? It's approximately 500. It's somewhere in the vicinity of 500. Just like this one is somewhere in the vicinity of 2. And this one here, after 20 flips, by the way, proportion of heads, 20%, right? 2 out of 10. After 20 flips, remember the first 6 are tails, leaving 14 flips to go,
So 7 heads and 7 tails.
it should be approximately a total of 7 heads after 20 flips. Right? 7 and 7, and these 6.
Oh, okay.
And this will be 0.35, 35%.
Wait, can you repeat that one more time? Why
The first 6 flips are tails, correct? So we have how many flips to go up to number 20? How many
14.
more flips? How many more flips are there? 14, right? Yes, 14 flips. And of those 14 flips, how many heads do we expect?
About 7.
About 7.
Okay, thank you.
Which means out of the first 20, we expect about 7 heads, somewhere in that vicinity, approximately 7.
So it'd be 7 out of 20.
So it'll be 7 out of 20, which is 35%.
Okay, thank you.
Now, once you get to 100 already, that's pretty large. At this point, I just say I would guess approximately 50. Okay, once you get to 100, it kind of overshadows 6 to the point.
Okay,
where-
so when it, like you said, once it overshadows that amount of flips that you
Yeah,
got,
yeah.
then
Then,
we just go generally, it's
Then
about
you-
15.
exactly. Then you just go to the
Okay.
law of large numbers and you have stabilization.
Thank you.
So do the number of heads and tails even out? Well, at least approximately, I would say yes.
Yeah.
Right? At least approximately. Listen, it's never going to be exactly 50-50 unless I'm really, really, really awesome. But it should be approximately yes. Does the how do you, I can't scroll now because if I, can I get maybe X out? There we go. Uh-oh. Uh-oh.
Just use your eraser on the annotate bar, and you can erase all that stuff.
Well, I don't want to. Oh, that's right. So it doesn't stay on the.
Right, it
It
doesn't.
doesn't
just-
stay. Okay, I gotcha. Okay, so
You can probably clear all the drawings. Yeah, there you are.
girl drawing. Okay, awesome. You guys are amazing. So then the question is, does the proportion of heads tend to get closer to a half? And the answer is yes. That's the law of large numbers. Okay, and by the way, here's what happened on the next 94 flips. So this is the actual experiment that was done. And here's what happened on the next 94 flips. What do you notice about the beginning versus the end?
It got closer to 50%.
It's getting closer to 50%, right? Very sporadic in the beginning, but it gets closer to 50%.
Professor, can you repeat that? I'm sorry, I keep getting kicked out of the meeting.
That's fine. Yeah, no problem. So
I'm sorry.
no, don't apologize. It's, it's technology. This is, that's the world. So here are the first 6 flips. 1, 2, 3, 4, 5, 6. Then a heads, tails, heads, heads, right? It goes up its heads and tails, down its tails, right? So heads, tails, heads, heads, tails, tails, heads, heads, and we have this whole shape here, right? Lots of sporadic motion in the beginning. But over the long haul, what do we see? It's getting closer and closer and closer to what number? To 50%, because that is the law of large numbers, right? As you get closer and closer and closer, you get closer and closer to 50%. I mean, as you get further, you get closer to 50%. Does that make sense?
Yes.
So how many heads actually were there after 10 flips?
3.
There were 3. We had guessed 2, but there were 3. That's why I said approximately 2. I can't tell you exactly how many there are going to be, but it should be somewhere around 2. In fact, it was 3. How about after 20? Let's count them. 1, 2, 3, 4, 5, 6. So I had guessed 7 as an approximation. There were 6, pretty close. How about after 100? Well, do I really want to go through it all? Not really.
Oh.
But it looks like I ended about 47%. And if I truly ended 47%, that would be 47 heads. Right? 47 out of the 100, which is close to 50.
Yep.
Okay. So does the graph illustrate the law of large numbers? Yes, again, it does, because even though you have a lot of sporadicity in the beginning, as you move further down the line, you get closer and closer and closer to
Is it closer to the theoretical probability?
Yes, exactly.
Okay.
Exactly. That's okay. And Miriam, thank you. You're here. That's wonderful. I know you're a few minutes late, but you're here. Okay. So next slide. So everything we did so far was empirical. You're basing your estimation of the value of the probability based upon actually performing an experiment or looking at somebody else's experiment. But now we're going to look at theoretical probability. And theoretical probability is all about common sense. It's about asking yourself, without actually doing any experiment, what do I think the likelihood is just based upon my experience on Earth? Or if you go into space, in the universe.
Can I ask a question?
Yes, of course.
On Monday we went over like the dice problem where it was like you roll a die 100 times and get 3 out of 21, and then you had the empirical probability as 21 over 100, and then the theoretical as 1 over 6.
Yes.
What's the 1 over 6? Because like you have one chance to get a 3 on a dice.
Well, that's what this page is about. Yes. So let's go over this page, and that's exactly what we're referring to.
I was confused.
Yeah, that's exactly what this is.
Okay, thank you.
Okay, so it says theoretical probability in grades K through 8 often involves making lists of equally likely outcomes. Now, in the case of the die, how many equally likely outcomes are there?
6.
6. And how many of them were the number 3?
1.
1. So the theoretical probability of getting a 3 is 1 out of 6. I'm not actually rolling the die. I'm not performing this experiment. I'm just using common sense. But common sense only holds like this if it's equally likely outcomes. I gave an example yesterday in my other class. Someone said, anytime there's 2 outcomes, it's automatically equally likely. This is what he says. And I go, really? I said, let me ask you the following question. If you walk outside your house to the front, you're outside your house, and you look at the next car that drives by, what is the likelihood that the driver is a male versus a female? And he said, well, it's 50-50. And I go, yeah, you're right? 2 outcomes, male or female. And I don't think there's any reason why there'd be more of one versus the other, and everyone drives, right? There's no more people who drive of one gender versus the other, right? Then I said the following. Suppose I don't care if it's a male or female. Suppose I care about their age. What's the likelihood that the person who drives by next is over 100 years old? And he said, not very likely. And I go, but there's only 2 outcomes, more than 100 or not more than 100? What do you mean? 50-50. He goes, yeah, but they're not equally likely. I'm like, that's the whole point. Just because you have 2 outcomes does not mean they're equally likely. One could be a lot more. Okay, what's the likelihood that the pandemic ends tomorrow? Not great.
0.
Pretty much. Pretty much, right? It's not great. 2 outcomes, either it does or it doesn't, but one is a lot more likely than the other. So it's very important when you look at the rules on this page that you understand that we are dealing with equally likely outcomes. And if those outcomes are not equally likely, you cannot apply most of the rules that we're going to learn about. So you have to recognize when a rule holds and when it does not hold. And if it does not hold, you either learn new rules or you say, you know what, this is too difficult for me, I'll let someone else handle it. And there's nothing wrong with that. There's a lot of smart people in this world, a lot smarter than I am. And you know what? Let them do it. Okay? As long as somebody's figured it out, why does it have to be me? That's how I feel. Okay? So let's look at the rules of basic probability on this page. Okay? This is, you can see it's very important because it's in a box. It's even more important, it's highlighted in bold. Okay? So you're talking about a box and highlighted or bold, you know it's important. The basics of theoretical probability. First of all, probability is a number between 0 and 1. Any probability you ever find in any problem that you ever do in any course in your entire life It'll always be a number between 0 and 1. If you get as an answer something that's not between 0 and 1, what can you conclude? What?
It's not the probability.
Well, you can conclude that you made a mistake. Right? That's what you can conclude. You did something wrong. Because probabilities must, and I mean must, be between 0 and 1. It's impossible for it otherwise, because think about it. 0 means 0%. It's essentially impossible for it to occur if its probability is 0%. That's what 0 means. 1 means 100%. It's definite that it's going to occur. Well, you can't get any less likely to occur than impossible and more likely to occur than definite. Okay, you might have heard, oh, I gave it 110%. That's an expression people use to indicate they tried really hard. You can't really have 110%. However, if I invest money, my return could be 110%. That's fine. You can get a return. Yeah, if I put $100 in and I get $210 out, I made more than 100% of my money. Right? I got more than my money back. I got more than that. You can have a return of greater than 100%. So I don't mean to say that you can never have 100% in your entire life, but not on probability. Now, it could be a fraction, it could be a decimal, it could be a percent. I don't care. Whatever's easiest for you, but it has to be between 0 and 1. That's rule number 1. Bullet. Got a little black box to the left. Back. Really important. Does that make sense so far?
Yes.
Okay, next. An event is a set of outcomes from a random situation. Now, this is very important. What is a random situation?
Maybe like running into someone you haven't seen in a long time.
Well, that would be random, but that's not what we mean. When we mean a random situation, it means the following. I mean, yes, that is random. Like, my God, that was so random. That's not what we mean. A random situation is very specific in probability. It's when you perform an experiment or something occurs, doesn't have to be a physical experiment, something occurs, where you do not know what the outcome is going to be in advance. But you do know all of the possible outcomes.
Okay.
Okay, you don't know what it's going to be, but you know what it might be. An example, rolling a die. I don't know what I'm going to get, but I know what I might get.
Okay.
Right? Flipping a coin. I don't know what I'm going to get, but I know what I might get. What's another example of a random situation? Huh?
Pulling out of a hat.
I'm sorry?
Like if you pull out of a hat of like different choices.
Sure, right? You put everyone's name in a hat. You flip it around. I'm going to pick someone who's going to win a prize, right? I know exactly what it might be. Everyone's name's in the hat, but I don't know what it's going to be. That's a perfectly random situation.
Secret Santa.
Sorry?
What about Secret Santa?
Well, Secret Santa means you don't mean what you're going to get, but you mean who's going to give it to you, right?
I guess.
Okay, yeah. I mean, if you're in a secret, I'm Jewish, so I don't know about this whole Secret Santa thing. But if you have a secret Moses thing going on, then
essentially it's the same thing.
Okay, I just made that up. So I don't even know. I know. I'm just kidding. I know what it is. Yeah. But like everyone's name is in the pool, and you don't know who's going to give to who, right? But you know someone's going to give to you, unless of course you're the one that nobody likes and nobody wants to give you anything.
Mm-hmm.
It has happened. I've been that person. But anyway. What are some other examples?
The spin wheel.
A spin wheel, like roulette or something?
Yeah, that or the ones that the kids use in math class.
Sure. Yeah, sure. How about
Twister?
Or Twister. How about giving birth?
Ooh, yeah.
Right? You know, boy or girl, you don't know what?
Yeah, 50-50.
Well, for that situation, you'd probably want to look at your empirical data to decide.
Oh.
And I don't think it's 50-50. I think it's more like 48-52 or something like that. I think girls are a little more likely than boys. But either way, it's pretty close. It's pretty close. So there's lots of situations of random situations. And the key for all of them is I do not know what I'm going to get, but I know what I might get. Now, an event is a collection of outcomes from a random situation. It doesn't only mean one. It could be a collection of them. So for example, if I roll a die and I say my event is getting an even number, then which outcomes would fall under the purview of this event?
Whatever event is an even number?
Well, I roll a die, right? We've all rolled a die before, correct?
Oh, for a die.
Yeah, I roll a die and I say my event is getting an even. So which outcomes,
3 out of 6.
No, not how many. That's another question. I'm asking for the actual outcomes that would fall under getting an even.
You could get a 2 or a 4 or a 6.
There you go.
Or a 6.
Yes, yes. There are 3 outcomes, it's true. But the event is getting a 2 or a 4 or a 6. That is the event. Okay, I can say getting a prime number. How many prime numbers are there on a die? Anyone know? And just be aware of the fact that most people get this wrong, but how many prime numbers are on a die?
3.
3. What are the 3?
Is it 1, 3, and 5?
What happened to 2?
2 is a prime number too, so 4.
Okay, but you're both wrong, but thanks for playing. Because one is not a prime number.
Isn't it 2, 3, 5?
2, 3, 5. Those are the 3 primes. That's correct. 1 is not a prime number.
I thought it was. Okay. I'm wrong.
So you just learned something. You just learned something. It's okay to be wrong. That's when you learn. If you're right all the time, like I don't learn anything anymore. I'm always right. So being wrong is amazing because you get to learn things. Okay, so why is 1 not prime? It's really not important why, but just know that 1 is not a prime number. Okay? The rule is that 2 numbers have to go into it, not just 1. So 2 is prime because 1 and 2 go in. 3 is prime, 1 and 3 go in. 4 is not prime because it's 1, 2, and 4. And 1's not prime because it's only 1.
Okay.
It has to be 2. Anyways.
Okay.
I just Googled it. It says a natural number greater than 1.
A natural number greater than 1, right? So a prime number is a natural number greater than 1 that only has 2 divisors. That only has 2 numbers go into it. Trust me on this one, I'm a doctor. But anyways, let's move on. So an event is a collection of outcomes because sometimes you don't care about one outcome by itself. You care about a collection of them. An example might be, suppose you roll a die. It's a very simple situation. Suppose you roll a die and you're playing Monopoly. Okay, so you guys ever play Monopoly? Everyone's played Monopoly at some point, right? I hope so. I mean, it's a horrible game when you're older and you realize, my God, how dumb it was. But when you're a kid, it's a lot of fun until you start cheating. Then it's horrible. But anyways, so you're looking at the Monopoly and you look down and you're like, if I land there or there, I'm in trouble. So I hope I land in one of the other places. In that situation, it's not just one outcome that matters, right? It's a few outcomes that matter. And you're hoping not to be in any one of them. So you're looking at the collection of outcomes. And the question is, how likely is that collection? Not a specific one, but that collection. That's a more important formula than just one. So that's what an event is. Does that make sense?
Yes, I just have a question. What does N stand for?
Where do you see N?
N as in Nancy.
Oh, we haven't gone that far yet, so let's not worry about that.
Oh, never mind.
We haven't gone there. Okay. Well, wait till I finish, and then if you still have a question, I'm more than happy to answer. So the third bullet says an event that cannot happen, it is impossible, has a probability of 0. Fourth one says an event that is certain has a probability of 1. Does that seem reasonable? If it cannot happen, 0% chance. And if it's certain to happen, that's 100% chance. Correct?
Mm-hmm.
Those two seem reasonable, right? Now, here's the key. If the outcomes are equally likely, which is not always the case. But here, if the outcomes are equally likely and there are n of them, what does n stand for? Some number. Could be 10, could be 5, could be 1,000,000, could be 6, could be 2. I probably wouldn't care if it's 1 because then it's not a random situation, right? So chances are n is 2 or more.
Can I ask a question?
Yeah.
Sorry. So, like, you know how you said it has to be between 0 and 1?
Yes.
Okay, what if it was like you're rolling a dice and like what was the chances of getting an even number? So it's 3 out of 6.
Right? 3 out of 6 is between 0 and 1.
Isn't that
3 out of 6 is a half.
okay, hold on. Never mind.
Right?
I was thinking like decimal, like 0.5.
0.5 is also between 0 and 1.
Well, yeah, but I was, okay, sorry.
It's okay. Ask away if you don't understand something. Nothing's wrong with that. Just, you know, if something is not making sense, clarify it on the spot before we go on. Okay? So, if the outcomes are equally likely and there are n of them, then each outcome has probability 1 over n. Let's look at the die. 6 outcomes. What's the likelihood of getting a 1?
1 out of 6. So,
1 out of 6. Getting
so
a
it would be P of A equals 1 out of 6?
Well, you have to define what A is first. You got to explain what A is. So in this case, I would say let A be the event getting a 1.
So P of getting a 1 out of...
Nope. P of getting a 1 equals...
1 out of 6.
1 out of 6.
Okay.
Right?
So if you were to write it, would you write P of 1 equals 1 out of 6?
That's correct. And I can say P of even equals
3 out of 6.
3 over 6. And if I'm flipping a coin, I can say P of heads equals
A half.
1 out of 2.
I just wanted to clarify. So A stands for events.
A stands for some events, which you're going to tell me what it is for that problem that you're dealing with.
Okay.
It could be getting a heads. It could be getting a 1. It could be getting an evens. It could be having a boy. It could be raining. It could be anything that's random. A is that event. The probability of getting that event, assuming that they're equally likely outcomes, again, this has to be for equally likely outcomes, is a number of ways of getting the event divided by the number of outcomes that are possible. So if I want to get an evens, there's 3 ways of getting an evens, and there's 6 outcomes, so 3 out of 6. If I want to have a boy, there's 1 way of getting a boy, and there's 2 outcomes, so 1 over 2.
Is it just between 0 and 1, or can it be like 0 and 1?
Well, it could be 0 for something that's impossible, and it could be 1 for something that's certain.
Okay,
Right?
thank you.
Those are the 2 bullets that were above it. Does that make sense?
Yeah. Oh, yeah.
Right? And then there's the last bullet. The last bullet says, the probability that an event does not happen, the probability of not A is 1 minus the probability of A. Let's think about that. What's the likelihood of getting a 1 if I roll a die?
1 out of 6.
1 out of 6. What's the likelihood of not getting a 1 if I roll a die?
5 out of 6.
Which is 1 minus 1 over 6. They have to add to 1 because either you're going to get it or you're not going to get it. Right? The 2 of them have to add to 1. So sometimes it's easier to calculate probabilities by calculating the not rather than the regular. It's a little backwards, and we'll see if we have a situation like that. I don't want to spoilers, no spoiler alerts in this class. When I teach, I like to pretend that I have no idea what's going to happen next and be just as surprised as you. So we'll see if we actually deal with a situation like that. Okay, but the probability of not having an event is 1 minus the probability of having that event. And we call not A, we give it a name, we call it the complement of A. So I can say something like, what is the probability of the complement of A? I'm just saying, what's the probability of not A? Okay? Let's do an example and see this in action. So here's an example. Each student in Math 211 writes his or her name on a slip of paper. We put them all into a hat and we, shake up the hats. We draw one slip at random. Let event F be getting the name of a female. What is the number of possible outcomes? N. Well, to answer this question, we'd have to know one thing.
How many people there are in the class?
How many people there are in the class. Now, when I teach this class in a live setting, it's easy. I just count, okay, 1, 2, 3, 4, here it's a little more difficult. So let's just say there's 45 people. All right, let's just make up a number. Let's say it's 45 people. It's probably somewhere in the vicinity of the correct answer. So let's say there's 45 people. That's N for this problem. Lowercase n is the number of possible outcomes 45.
Mm-hmm.
Now it says compute the probability of getting F. What does F stand for in this situation?
A female name.
A female. Now, to answer this question, what do we need to know?
How many women there are?
How many women there are, right? Let's assume, for the sake of this example, that there are 33 women in the class. Okay, and again, I know that there's, identifying as a woman or biological. I'm not getting into those details. It's just straight up. This is for K through 8, so straight up to keeping it simple, female versus male. And I don't even care which way it is. It's just an example. Okay, so let's say that there's 28 females. Sorry, what did I say, 33?
Yeah.
33. So what is the probability of getting a female in this particular example? What does P of F equal to?
33 out of 45.
33 over 45. Done.
0.
Can you simplify that? Yes. Can you make it a decimal? Sure. Can you make it a percent? No problem. They're all equal. But the straight up answer, 33 over 45.
Mm-hmm.
Now, what is the probability of not having a female?
So 45.
45 minus 33.
1 minus,
Oh.
1 minus the fraction that we just had.
So it would be 1 minus 33 over 45.
1 minus 33 over 45, which then simplifies to what?
0.7.
Keep it as a fraction. Keep it as a fraction. What is 1 minus 1 minus 30?
Is it 12 over 45?
12 over 45. Because how do you subtract 1 minus? I'll do it here. Hold on.
Yeah.
Annotate. We have 1 minus 33 over 45. So how do we do that?
Don't you just turn it into 45 over 45? The 1?
Well, the 1 is the same thing as 45 over 45. Now it's also 22 over 22. It's also 17 over 17. It's also, 71.3 over 71.3. Why did I pick 45? Because I want the denominators to be the same.
Right.
All right, I want the denominators to be the same. And once the denominators are the same, then I just straight up subtract the numerators. 45 minus 33 is 12, and the denominator remains 45. Of course, that's a mathematical way of doing it. There was a much easier way of doing that, which is what? What's a much easier way of doing it?
Calculator?
No, even easier than that.
45 minus 33.
Even easier, well, yes. Because if there's 33 females in the class, how many males are there?
Right.
Right? There's 12. Right?
So 45 minus.
I would have immediately jumped to 12 over 45. Does that make sense?
Yes.
Okay. So let's clear that. How do I just clear all drawings? Okay. Are the events female and not female equally likely?
No, because there's more girls than guys.
There's more girls than boys, right? So they're not equally likely. 33 over 45 is somewhere around 70%, give or take, 60 something percent.
71%.
71%, and not 12 over 45 is like what, 29%. So no, they're not equally likely. Does that make sense so far? All right.
It would be equally likely if it was exactly 50-50.
That's right. And only exactly 50-50.
Okay.
Now, is it possible that some other Math 211 class would answer that question? Yes, they're equally likely because their class happened to be 50-50? Sure. We went on my example. Okay, so you can't compare this to another class and assume you get the same thing. So next thing we have is something called the sample space. The sample space is the collection of all possible outcomes of a random situation. It's not how many outcomes there are. When I ask for the sample space, I'm not looking for, oh, it's 6. The sample space is literally the outcomes themselves. And the outcomes must be disjoint, i.e. mutually exclusive, so that no two outcomes can be listed. Well, you don't want to list 2 different outcomes for the same situation.
Does that mean that each outcome is only allowed to happen once?
That means that when you write down the outcomes, you don't want to write the same outcome more than one time. Now, you might think, why would I ever do that? You'll see what I mean in a second. So here's an example. You ask your 5th graders to write a sample space with equally likely outcomes for the situation of flipping a penny twice. Here are 5 different responses. The first one says 2 heads, 1 head and 1 tail, 2 tails.
Okay.
And wait, I didn't say that's right or wrong. I just said that's what the first one says. 2 heads, 1 head and 1 tails, 2 tails. That's what the first one says. The second one says a head then a tail, a head then a head, a tail then a tail, and a tail then a head. The third one says H, 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 T, T, H, T, T. The second and the third are basically what? The second answer and the third answer are basically what?
They're the same ones.
They're the same, it's the same answer, right? When you say H, H, we obviously know that means heads, heads, right? Use your brain, right? Second and third are really the same. The third one's smarter because he used less ink on his pen or her pen. So got the same point across with less work. Then there's 4. 2 of the same, 1 of each. And the last one says it could be 0 heads, it could be 1 head, or it could be 2 heads. Now, we already established the second and the third is the same answer. Are there any other of these 5 that are really the same answer?
No.
Number 1?
Is it 1 and 4?
Well, I was thinking immediately 1 and 5. Because 1 and 5 says 2 heads, and the last answer literally says 2 heads, right?
Okay.
Then says 1 head and 1 tail, which is essentially 1 head. And then says 2 tails, which is essentially 0 heads.
Oh, okay.
So 1 and 5 are really saying the same thing, just in different words.
Yeah.
Right?
Right.
Now, number 4 is also kind of saying the same thing as 1 and 5. It's saying 2 of the same and 1 of each. But the problem is for the 4th one, 2 of the same is really covering 2 different possibilities, 2 heads or 2 tails. Right?
Yeah.
So all five really describe the situation well. Right? I know exactly what's happening for all 5 of these answers. But the question is, which of these are sample spaces? So let's again look at the definition of a sample space. A sample space gives all possible outcomes. The outcomes must be disjoint, meaning no more than one of the outcomes listed can occur on the same situation. So the question is, which of these 5 are sample spaces?
Definitely the third one.
Definitely the third one, right? The third one has 4 different outcomes that are all different. And because we've established the second and the third are really the same thing, then definitely the second one. Okay?
Would the fifth one count or no?
Which one did you say? I didn't hear what you asked.
Would the fifth one count?
So let's look at the fifth one. 0 heads, 1 head, or 2 heads. So it does count, but we have to be very careful here. Because even though it lists 3 different possible outcomes, 1 head, 2 heads, or no heads, are those all equally likely?
No.
No, because look at the third answer. How many ways are there of getting 0 heads? If you look at the third answer, how many? Sorry?
I'm sorry, never mind.
If you look at the third answer there, H, 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 T, T, H, T, T, how many of those are 0 heads?
1.
Just 1. How many of them are 2 heads?
Just 1.
Just 1. How many of them are 1 heads?
2.
2.
Oh,
1 of them.
2, right? So they're not equally likely. It's a perfectly valid sample space. In fact, all of these are perfectly valid sample spaces. They're all perfectly valid sample spaces, but the problem is that they're not all, I wouldn't say it's a problem. They're all perfectly valid sample spaces, but they don't have equally likely outcomes. Now, is having equally likely outcomes better? Not necessarily. It's just a different way of looking at a problem. I personally like equally likely outcomes because then it's easier to work with it. But as long as your sample space lists the possibilities, it's a perfectly valid sample space. It all depends on what you're after. Are you after something like 0, how many heads there are? Is that your question? If that's your question, then it's either 0, 1, or 2. Those are the outcomes. Is your question more specific? What am I getting on each flip? Well, then just saying 1 heads is not enough because it could be HT or TH. And I want number 3 or number 2. Does that make sense? Okay.
so
Yeah.
just to kind of just go over the 2 questions at the bottom.
Sure.
The one that says which of these are sample spaces, is it all of them except number 5?
No, they're all sample spaces. They're all sample spaces. They all list the possibilities for the situation.
So for the answer to that question, we would write all of them.
All of them.
And then,
However, which of them have equally likely outcomes? That would just be which
3.
one? 3 and 4. Sorry, 2 and 3. I'm sorry. Oh, actually, well, let me read again. I just looked at 4 again, a little closer. 4 says 2 of the same, 1 of each. Right? 2 of the same has 2 possibilities, and 1 of each also has 2 possibilities. Correct?
Yeah.
So that one has equally likely outcomes as well. Okay. If the question is essentially, well, I don't really like the question. You're not going to have a question like this because it's a little vague. Me personally, I would always go to number 3 for a sample space. You're really breaking it down to its actual outcomes themselves. Every step of the way. Heads, 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 tails, tails, heads, tails, tails. Very easy to see what's going on. And the outcomes of each individual part of the experiment are very well written. But I'm not going to ask you something that's this vague because I don't like it. And if I have to think about it, then I don't think you should be responsible for it. Yes.
So then for number 1, if it had also listed, because it says 2 heads and then 1 head and 1 tail and then 2 tails, but if it also listed 1 tail and 1 head, then it would be.
Then it would not be a sample space because now you're listing the same thing twice.
Mm-hmm.
1 head and 1 tail and 1 tail and 1 head is saying the same thing.
But isn't it depending on the flips? The first flip can.
But it doesn't say 1 head then 1 tail. It just says 1 head and 1 tail.
Okay, got it.
So one head and one tail, and one tail and one head are the same thing.
Yeah, because it doesn't specify which one's coming first.
Right. That's why number two, a head, then a tail. A
Got
head,
it, okay.
tail, and so, okay. So now we have something called a probability distribution. Okay, a probability distribution lists every possible numerical outcome along with its probability. So for example, a very simple situation of flipping a coin, flipping two coins like the penny in the last example. Suppose I was interested in how many heads there were. Then there's only three possibilities, right? No heads, one head, or two heads, correct?
Mm-hmm.
Based upon the previous slide, right here, how many ways are there of getting no heads?
One way.
And how many possible outcomes are there?
4.
Four. So what would be the probability that I would put here?
1 out of 4.
1 out of 4. And how about for getting one head? How many ways are there for getting one head?
Well, if it's at least one.
No, not at least. One head.
It's 2.
2. So what would I put here?
2 out of 4.
2 out of 4. And how about for getting two heads, specifically two heads?
1.
1. So what would I put here?
1 out of 4.
1 out of 4. And you'll notice that when you add up these three numbers, what do you get as your total?
4 out of 4.
4.
Which equals?
1.
1. It always has to add to 100% because you got to get one of them.
Mm-hmm.
Right? It's got to be one of them, right? So it always has to add to 100%. I'm sorry, I just see here a text from a while ago. I apologize. N was 45. So yes, that's a long time ago. I'm very sorry. I'll hopefully figure out a way to see these things better. So here, example.
Professor, sorry,
Yes,
did you
yes.
just randomly choose like what sample space you wanted to use?
No, I wasn't even using a sample space here. I was using the same question, and I asked for the probability of getting 0 heads. I mean, if I use, these are the actual outcomes, right?
Yeah, so you just randomly chose number 3, right?
Well, I didn't randomly choose it. All of these are describing the situation.
Mm-hmm.
But this one, or 2, which is really saying the same.
Or 2. Okay.
These are really the best in the sense that I can see the individual outcomes themselves.
Okay.
I can't see them for the other ones.
Mm-hmm.
Okay.
Thank you.
So here's an example. Write a sample space with equally likely outcomes for the situation of flipping a penny 3 times. So let's go ahead and write a sample space with equally likely outcomes for the situation of flipping a penny 3 times. Write them out. I'll give you the first one. HHH. You write the rest of them. So, someone give me another one.
Tails, tails, tails.
Okay, tails, tails, tails. Another one.
H tail
H.
TH.
HTH. Okay. If I hold the writing.
ETH.
Which one?
ETH.
HTH we already have. Did you say that or something else?
TH
THH. Okay.
THT
THT.
HTT.
HTT.
HHH.
HHH is the first one.
Oh, I'm blind.
HT
Which one?
HHT.
HHT.
TTH.
And TTH. Any other ones?
I think that's it.
There's
Oh,
only
1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. Does that make sense?
yes.
Well, think about it. The first flip, how many outcomes are there? Just the first flip. Huh?
Should there be one more?
Well, 1 second. The first flip, how many outcomes?
3.
Two.
The first flip has 2 outcomes, heads or tails,
Okay.
right? Second, the first flip, how many outcomes?
2.
2. Second flip, how many outcomes?
2.
Third flip, how many outcomes?
2.
2 times 2 times 2 equals what?
8.
8.
Done. 8. 8 outcomes. Now, what is the probability distribution for the number of heads? So how many possibilities are there for the number of heads? That's horrible. But how many possibilities what's the lowest number of heads that I can possibly get?
1, 0,
0. I can get no heads. Next?
or 1,
1,
or 2,
or 2,
Or
or
3.
Now, what's the probability of getting that many heads? What's the probability of getting 0 heads? Well, how many of the 8 ways are there of getting 0 heads?
1.
1. Just 3 tails, right?
Mm-hmm.
So the first one is 1/8. How about for getting 1 head, specifically 1 head?
2.
3.
3. So 3. Probability 3
Over 8.
over 8. How about getting specifically 2 heads?
3.
3 out of what?
Out of 8.
Out of 8. And the last one?
1 out of 8.
1 out of 8.
Oh, it adds up.
It better add up if it's going to be a valid probability distribution. Now, what's the probability of getting 2 or more heads?
4 out of 8.
4 out of 8. 2 or more is these 2, 4 out of 8. Does that make sense? I'm clearing and go. And
Can you explain again how you got the number of probabilities with multiplication? I missed that part.
not probabilities, a number of outcomes. There's 3 flips. 1, 2, 3, right? 1, 2, 3. Each flip had 2 outcomes, heads or tails. Correct?
Yes.
So you multiply those. The first flip 2, second flip 2, third flip 2, 2 times 2 times 2, 8.
Okay.
It's like when you're getting dressed in the morning. You're deciding between 5 pairs of pants and 2 shirts. How many outfits do you have if you can pick 5 pairs of pants and 2 shirts? Well, each of the 5 pairs of pants can go with each of the 2 shirts, right? So this pair of pants with shirt A or shirt B. Second one with shirt A or shirt B. Third one, shirt A or shirt B. Shirt A, 5 times 2. It's the same basic idea. We'll do more of that later, I promise.
Thank you.
Okay. And then let's see how much more we have, because I think we're done. It's 8:14. We didn't quite finish chapter 1, so the homework is not due yet. But we'll end here and we'll finish it quickly at the beginning of next class and then move on. I don't want to already fall behind in the first week. But that's it for today. I will see you. I'll put the video up tonight. Where is the homework? The homework is about 3 pages low. There you go. Homework number 1 right there. The homework starts on the same PDF. So the homework is right here. Homework 1. All these are homework 1.
Are we submitting the homework to you?
No, you don't submit the homework. You just do it. Homework is not graded. Homework is not graded, but the quizzes and the tests are based on the homework. So do them, do them, do them. Okay?
And we will go over the homework, correct?
Well, I will answer questions that you have on them, but we're not going to spend class time going over every single question. We just don't have the time.
No, but that's what I meant. Question.
Yeah, if you don't understand something and no one was able to help you, then yeah, something we will go over.
Would you give us like an answer key to check all of our answers if we need to?
Yeah, I can do that. That's not a problem.
Okay, awesome.
I'll do that. Yeah. Okay. Sounds good, guys?
Yeah.
All right. Then have a good weekend. I'll see you guys on Monday.
I have a question for you.
Yeah, go ahead.
Because